Okay, so we have now talked about all the different ways of solving systems of equations by graphing, substitution, or elimination. And so now we're going to talk about another type of system that you might find, and not a system of equations, but a system of inequalities. So back when we were solving equations, we also talked about solving inequalities, less than or greater than, things like that. When we talked about our linear equations, we also talked about linear inequalities and what happens when we have to graph a line that doesn't have an equal sign, but a less than or greater than or something like that. So today we're going to combine all of that and what happens when we have two of those linear inequalities that we're going to solve at the same time. So we're going to learn how to solve them by graphing. That is one of the only ways to do it, or really the best way, is by graphing. And then we're going to learn how to figure out if a point is a solution to an inequality. So as a warm-up, let's go back and just think about from Unit 2 when we did one linear inequality and how we graphed that. So pause your video and see if you can remember. All right, so if you think back to Unit 2, we needed to make sure our equation was in slope-intercept form, right? Y equals mx plus b, even though it's not really an equal sign, but the same idea. In this case, it was already, so then we need to think about how we would graph the line if it was an equal sign. We say, well, m equals 1/2, that's rise over run, and b equals -3. So I begin with b, so I put my point here at -3 on the y-axis. And then I want to rise 1 and run 2 from that point. And I do it as many times as I can till I get all the way across my graph. And I could rise -1 and run -2 because two negatives make a positive. So that would work as well. And I could go this way. All right, now, we learned back in Unit 2 not to get too anxious to draw that line because this is where the inequality starts to come into play, right? I need to know, are the points on that line a solution or not a solution? And we tell that by looking at the inequality itself. This is just greater than. It is not greater than or equal to. So the points on the line are not actually solutions. So this would be like an open circle if it was just a single variable instead of two variables. And remember from Unit 2 that we represent that when I'm talking about a line with a dotted line. So I'm going to make sure that my line is dotted going through those points. So that was our first thing we had to do with our linear inequality, and that was different from our equations, right? We had to think about dotted or solid. So dotted was if there was no or equal to, solid if there was or equal to, right? So greater than or less than was a dotted line. And then less than or, sorry, my pen. Greater than or equal to or less than or equal to was a solid line. Solid line means those points are solutions. Dotted line means those points are not solutions, but everything right up to it was. All right, so then the next thing we needed to do is we needed to figure out shading. Remember our single variable inequalities, we shaded left or shaded right, and it was really easy to tell just by looking at the inequality. But when I put it on a line, left and right isn't really a thing anymore, right? So I need to make sure that I check a point. And the easiest point to check is the origin. So I plug in the point 0, 0 into my original equation. So it'd be 0 is greater than 1/2 times 0 minus 3. 1/2 times 0 cancels out, so I get 0 is greater than -3. Is 0 greater than -3? Yes, it is. So the point 0, 0 is a solution to that inequality, which means I want to be shading on the same side of the line that 0, 0 is on, because everything that's on that side would be a solution then as well, because anything in the shading is a solution to that inequality. So I want to make sure that my shading covers that point. Now when you plug in 0, 0, if it's not true, if it said 0 is less than -3, that's not true, then I would want to shade the other side so that the point 0, 0 is not shaded if it's not true. So if it is true, you shade the side that point is on. If it's not true, you want to shade the other side so that that side is not shaded. And there we have it. Okay, so remember, you graph the line just like you would if it was an equal sign, but before you draw the line, figure out if it's going to be dotted or solid. And then after you draw the line, you need to figure out the shading by plugging in the point 0, 0. Hopefully you remember all of that from Unit 2. That was a review. Because now what we're going to do is we're going to have two of them on the same graph. Now what I usually tell my students on this lesson is to get out some colored pencils and keep track. Do one entire equation in one color and then do the other equation in the other color. Not only will it help you keep track of what's what on your graph, it will also help you figure out what the solutions are when we're done. Okay, so get some colored pencils, some highlighters, pause the video if you need to, and dig those out. Markers if you have to, but really colored pencils are the best way to go because you can attempt to erase them in a pinch if you need to. All right, so just like when we were graphing our regular system of equations, I kind of split my workspace into two spots here. So I'm going to take my top equation and I'm going to go over here. X plus 2y is greater than 4. I'm going to take my bottom equation and go over here. So negative x plus y is less than or equal to 5. Now I picked red and blue, and I'm going to try and stick to those colors for my entire inequality. The work, the graph, everything. Here we go. So I notice on my red equation on the left here, it is not in slope-intercept form. So I need to start by moving things around. First, I'm going to subtract x. I get 2y is greater than negative x plus 4. And then I need to divide everything by 2. Now remember, the only difference between solving an equation and an inequality is whenever you divide or multiply by a negative number, you need to flip the symbol. In this case, I'm dividing by 2. That's a positive number, so I don't have to flip, but don't forget about that rule. So I get y is greater than negative 1/2 x plus 2. So for this equation, my slope is negative 1/2. My y-intercept is 2. So I'm going to start at the point of positive 2 on my y-intercept. I'm going to rise down 1 and run 2. Negative 1, run 2, and I'm going to do it as many times as I possibly can till I get all the way across my graph. Then I'm going to go the opposite way. Maybe I go up 1 and left 2. And I'm going to go all the way across my graph this way. Okay, now before I draw the line, I want to make sure that I check out my inequality. I'm just going to switch to a different color here so you can see what I'm looking at. This was just a greater than, not a greater than or equal to, right? So there's no underline, so this is not, these points are not solutions, so this would be a dotted line. So I'm going to make a kind of dotted or dashed or whatever you want to call it. All right, so I'm going to put my line through there. Now before I move on to the next one, I want to finish this one completely, all the way to the shading, okay? So I'm going to plug in the point 0, 0 into this equation, into my red equation here, and see if it's a solution. So plugging in 0, 0, I have 0 plus 2 times 0 greater than 4. Notice I went all the way back to my original equation here. 2 times 0 will cancel. I have 0 greater than 4. Is 0 greater than 4? No, it's not. So I do not want to shade on the side that 0, 0 is on from that line. I want to shade the other side because since 0, 0 is not a solution, it can't be in the shading. All right, so then I'm going to shade on the other side of my line from 0, 0. So it should look something like this. There we go. All right. Now I have that line completely done, so I'm going to try and tackle my other one. So now I'm looking at my blue line, the bottom one. This one also is not in slope-intercept form, so I'm going to start by moving my x to the other side. I get y is less than or equal to x plus 5. All right, well that was all I had to do. That one was easy enough. So now my slope on this one, oh, the invisible 1. So my rise over run is 1 over 1, but they were all invisible. and my y-intercept is positive 5. So I'm going to put my point here at positive 5, rise 1, run 1. That one's pretty easy, but it means you got to make a lot of points. All right, now, if you were thinking about solving a system of equations, you would have noticed that we intersected at a point right there. But we're talking systems of inequalities, and that's different. Okay, now before I draw my line again, I want to really look at it and think, dotted or solid? On this one, I have the or equal to, so these points are solutions to my equation on this one. So I need to have a solid line for this problem. So I'm going to draw a nice straight line all the way through. I could have gotten my ruler out, but this will work. All right, solid line on that one, dotted line on the other one. Make sure you can tell the difference. Okay, and now I'm going to check my point on this one. Do you see how the two different colors really helps? Because it could get very confusing on your shading and things otherwise. So now here's my 0, 0 from this line. I'm going to plug my 0, 0 into the original equation. Negative 0 plus 0 is less than or equal to 5. So that gives me 0 less than or equal to 5. Is 0 less than or equal to 5? Yeah, it is. 0 is less than 5. We're good. So that means I want the point 0, 0 to be in the shaded part of my blue line here. So I need to make sure that I shade the side of the line that has 0, 0 on it. So it should look something like this. All right. We'll get it all shaded in. All right, so these are not short problems, but hopefully they're not too difficult. Most of it's review. You're just doing it twice, right? Okay, now, remember that a solution to a system of equations is the point where the two lines intersect, right? It's the point that works in both equations. Now, when I'm talking system of linear inequalities, that's different, right? Because when I have one of them, any point in the shaded region is a solution because I have that less than or greater than, right? It's not just the points on the line that are solutions. It's any point that's in the shaded region. Now, if I want a point to be a solution to the system, it needs to be a solution to both of those inequalities. So maybe you can tell by looking at the graph, I mean, hopefully you can, where we would be looking for our solutions. So what I have on this next slide is the exact same system. This is the system that we just graphed. But now I couldn't fit all these questions on the same slide. So we want to think about, are these points solutions? So remember, a solution to the system means that it works in both of the equations. So the first point is the point negative 5, 8. So negative 5 is x, right? And 8 is y. So I could plug it into both equations and see if it works. So I would have negative 5 plus 2 times 8 is supposed to be greater than 4 for my top equation, right? That's this one. Well, let's see. Negative 5 plus 16 greater than 4. That would be 11 greater than 4. Yeah, that works. 11 is greater than 4. But now let's check the bottom one down here. So now I'd have negative 5. Careful with those negatives on that one. Plus 8 was our y, is less than or equal to 5. Two negatives, negative, negative 5. That's positive 5. Plus 8 is supposed to be less than or equal to 5. Oh, no way. 13 less than or equal to 5? No. So this point is not a solution to the system. Let's just go back and check where that point was on the graph. So here's the point we're looking at, negative 5, 8. Let's look at where it was on the graph. Negative 5, up 8. Right there. So I notice that was in the shading for my red equation. Yes, I did find that it was a solution for the red equation, but it's not in the shading for the blue equation. I found that it was a no. So this is not a solution to the system. It's only a solution to one of the equations. So not a solution. Okay. Now the next one is the point 2, 3. So again, 2 is x, 3 is y. And we could plug it in and see if it works, right? So on my top equation, my red one, I would have 2 plus 2 times 3 is supposed to be greater than 4. 2 plus 6 greater than 4. 8 is greater than 4. Yes, it is. That is a solution to that equation. Now let's check our blue one. Negative 2 plus 3 is supposed to be less than or equal to 5. Negative 2 plus 3 is 1. Is 1 less than or equal to 5? Yes, it is. All right, now let's go and check where it is on the graph. We're looking at the point 2, 3. Right 2, up 3. Right here it is. Look at where it is in the shading of our graph. It is in the shading of the red line, right? It is also in the shading of the blue line. So this is in the double shaded area. And this is where my solutions land. So the solutions to my system is any point in the double shaded area, right? And it's only a solution to the system. If it lands on a line, it's only a solution to the system if that part of the line is in the double shaded and it's a solid line. So be careful about that, right? But really what you're looking for, that's super tricky. Really what we're looking for is any point in the double shaded area. Solution. So now that we know that, I mean, we really have kind of checked too by showing all the work. The goal is, the reason that we graph this is so that we don't have to plug those numbers in and really check up. We can just look at the graph to figure out if I have a solution or not. So I really don't want to have to show all that work ever again unless it specifically tells me to show the work. So right now, if I just want to see if a point is a solution or not, I'm just going to look at the graph and find out where it is. So let's grab another color. How about this color here? And let's look at where the point negative 2, 3 is on our graph. Left 2, up 3. Oh, that's a tricky one. Now, it is right on the blue line, and it is right on the red line as well, right? Now, if this was a normal system of equations, you better believe that would be a solution. But look carefully at these lines. That would be a solution to the blue line because the blue line is solid. But the red line is dotted, and since it's on that line, those points are not actually solutions to the system, right? Or to the equation. It's everything right up next to it, but not that. It's like an open circle. So this really should not be a solution. But I'll show you what happens when you plug this into that red equation, since that's the one in question. Oops, not a solution. There we go. So if I plug in my negative 2 for x and my 3 for y into that red equation, it'll be negative 2 plus 2 times 3, and that's supposed to be greater than 4. Oops. So negative 2 plus 6 is supposed to be greater than 4. This says 4 is greater than 4, but take a look, be careful, look at that symbol. It's not greater than or equal to, it's just greater than. And so this is not a solution. And as soon as you find out that it's not a solution to one of the equations, you don't even have to check the other one, because for sure it's not a solution to the system. But that's why that one wasn't an or equal to, and so then it's not a solution to the system. Now, if both of your lines were actually solid, they both had underlines under the symbols, then that one would be a solution. That's a very tricky point. In general, you're looking for solutions to be in that double shaded area. Do you see why using 2 different colors for those problems will really help you find that double shaded area as well? All right, Let's try another system here. Same process where we graph an entire line, shade it, and then start on the other one. So again, I'm going to split my workspace. I'm going to take the top equation and put it on the left. Negative x plus y is greater than 3. I'm going to take my bottom equation and put it on the right. Negative x plus y is less than or equal to negative 5. All right. Red equation first, not in slope-intercept form, so I have to move the x first. So I get y is greater than x plus 3. My slope is that invisible 1 again, so rise 1, run 1. My y-intercept is positive 3, so here I am at positive 3. Rise 1, run 1 all the way across. And then go the other direction. Hopefully you guys are feeling really confident in graphing lines at this point. Okay, now before I draw the line, I do a quick check again. Dotted or solid. No underline here, so this one is going to be dotted. So we'll kind of connect every other one here. We'll make a nice dotted line. All right, there we go. And now before I'm done, I need to do the shading. So I'm going to pick the point 0, 0, there it is. And I'm going to plug it into my original equation. Negative 0 plus 0 is supposed to be greater than 3. 0 is greater than 3. No, 0 is not greater than 3. 0 is less than 3. So since that is not a solution to that inequality, I do not want to shade that side of the line. I want to shade the other side of the line. All right. Got my shading done here. Okay, so anything in that red shading is a solution to this inequality, but now we got to graph our second inequality to find our solutions to the entire system. So I look at that next one, negative x plus y is less than or equal to negative 5. That is not in slope-intercept form either, so I'm going to add x to both sides. I get y is less than or equal to x minus 5. Slope is my invisible 1, so 1 over 1. Y-intercept is negative 5. So I'm going to start with my point at negative 5 on the y-axis. Rise 1 and run 1 from there. All right, could go the other direction all the way across my graph. Now before I draw my line, I need to check. Less than or equal to on this one. So this is going to give me a solid line, and those points are solutions to that inequality. So I'm going to draw my line right through there, make sure it's very obvious that it's solid. Okay. And now I want to check that point 0, 0 in my blue equation as well. Negative 0 plus 0 is less than or equal to negative 5 for this equation. Is 0 less than or equal to negative 5? No, 0 is not less than or equal to negative 5. 0 is bigger than negative 5. So I do not want to shade that side. I want to shade the other side of my blue line. So this side will have the shading. Now, remember, we found out in our last system when we graphed it that we're looking for the part of the graph that has both shading on it, the double shaded area. Is this graph going to give a double shaded area? No, it's not. There's never going to be double shaded area on this. So this one would really have no solution. Now, when you were thinking of systems of equations, anytime we got parallel lines, right? Same slope, different y-intercept. Every time we got parallel lines, there was no solution. Here it's looking like this could possibly be the same thing. Maybe your brain is working a little bit though and thinking, wait, is there a possibility where I could have parallel lines that would still have a solution? Let's see. I wonder if this is going to come up here. All right, so This is going to be our last one. Really, hopefully you're feeling confident in this by now. If you'd like to pause your video and do this one on your own, you're more than welcome to do that. Top equation over here on the left, x plus y is greater than negative 4. Bottom equation on the right, x plus y greater than negative 1. Let's put that top one in slope-intercept form, so I have to subtract x on both. I get y is greater than negative x minus 4. My slope on this one is negative 1. My y-intercept is negative 4. So rise negative 1, run 1 this time. So I'm going down 1 and right 1. My line should be going downhill. And then I could go the other direction. All right. Check my inequality. My inequality is greater than, no or equal to. So this one is dotted again. Oops, sorry about that. There we go. All right, make sure it looks dotted here. I like to just connect every other one, especially when they're this close. Makes a nice dotted line. All right, and now before I do anything else, I gotta make sure I do my shading. Here's the point 0, 0. Plug that in. 0 plus 0 is supposed to be greater than negative 4. Is 0 greater than negative 4? 0 is greater than negative 4. Yes, that one works. So let's shade the side of the line towards 0, 0. So make sure that I get that point in my solution area. We're shading towards 0, 0 since it did work in this inequality. There we go. Okay. So my red line is done. Now I move over to the blue. Again, not in slope-intercept form, so I'm going to subtract x from both sides. I get y is greater than negative x minus 1. My slope on this one is also negative 1 over 1. My y-intercept is negative 1 this time, though. So same slope, different y-intercepts. I should have some parallel lines, and I believe that's what's going to happen here, right? Now, you notice already how this looks a little bit different? I can see that I'm most likely going to have some space that has a double shaded area for some solutions, no matter which way I end up drawing this line. But let's find out what happens. Checking for dotted or solid here. My inequality is greater than, so this will be dotted because there is no or equal to. So making it a nice dotted line here. Now this one is a little bit tricky for when we get to our shading, but make sure we have a good dotted line. Arrows on both ends. All right, now here's the point. That point is not actually on the line. It's just next to it, so we can still use 0, 0. 0 plus 0 greater than negative 1. Is 0 greater than negative 1? Yes, it is greater than negative 1. So I want to shade on the side that 0, 0 is from here. Whoa, so I have a really big section that's double shaded. This whole part all over here will be double shaded. So I have a ton of space that is that would have solutions to this system of inequalities, right? All of these guys, this whole thing over here, these are solutions. So when we have a system of inequalities, parallel lines don't mean necessarily no solution. It means you have the potential for no solution, right? If your shading goes in different directions, there's no way that shading is going to intersect from parallel lines. But if your shading doesn't necessarily go in different directions, then you could still have solutions to the system when you have parallel inequalities. So be careful of that. All right, so just again, remember, just to kind of wrap it up, make sure both equations are in slope-intercept form. Be careful about flipping the symbol when you multiply or divide by a negative. Decide on solid or dotted lines for each. Solid is or equal to, dotted if it isn't. And then shade each inequality. Plug in a point to see if it's a solution or not, and shade that direction if it is, the other direction if it's not. Remember that the origin is the easiest point to use. And then the solution to the system is in the double shaded area. All right. Hopefully you are ready to graph your linear inequalities, your systems of linear inequalities.